So data recover பண்ணவே முடியாது. Heat react பண்ண முடியாது. மத்தது பண்ணலாம்ல.
Good afternoon, everyone. Welcome to week 10 live session on structural dynamics course. I am Danish Bashir. So today in the week 10 live session that's going on the NPTEL website, the module 1, 2 and 3 are being discussed there, which discusses the topics regarding vibration of continuous systems, shear behavior and bending behavior, as well as generalized single degree of freedom systems. But in today's live session, we will be again discussing the topics which are being taught in week 8 sessions of NPTEL, multi-degree of freedom systems. So in the earlier last week, we studied how to derive generally governing differential equation of multi-degree of freedom system, wherein we derived the governing differential equation system of equation for a frame which was having two degrees of freedom. So we will be today solving some of the problems regarding multi-degree of freedom system, in which we will deal with 2 degree of freedom systems and 3 degree of freedom systems as well. Also in the last week, I also showed how we can derive the natural frequencies of the given multi-degree of freedom system, as well as the mode shapes. Regarding the same, today we will be solving some examples. As a first problem of today's session, we are having here a spring mass system wherein we have two masses m1 and m2, both are equal to m. These are connected by three springs, k1, k2 and k3. K1 is attached at the top and k3 is attached at the bottom, and these two springs are attached by k2.
ஒரே ஒரு டைம் சொன்னா கடைசியா ஓகே பண்ணுங்கன்னு சொல்லிட்டான். நீ பண்ணு.
These two masses are attached by spring k2. So in the question, it's also given that we have to take the value of n is equal to 1. N is equal to 1, that is k2 is equal to also equal as k. Where k2 is also equal to k. So we are having three springs and two masses, and there are 2 degrees of freedom systems. Here you can see that x1 of t and x2 of t. Since only two independent displacements are required to express all the inertial effects of this system, so we can treat this system as 2 degree of freedom. So in the last class, I already showed how we can derive the governing differential equation by writing the by drawing the free body diagram for each mass. So if I draw the free body diagram for each mass, we have one mass m is equal to like this m, and so for it's having one spring at above. So when it will be having displacement downwards, it will be having one force like this, this one k1 x1, okay, like this one, and then for k2 it's a relative displacement there. We will be having k2 x2 minus x1. I showed you last week. Here we have x1 of t, okay. And one more thing, we will be having in the opposite direction of the motion, we also have to give a Fichte law, which is proportional to the mass of system and acceleration of that point mass x double dot of 1. Okay, this is the free body diagram of mass. M1. Okay, FBD. So similarly, when we write the summation of f of y along the vertical direction is equal to 0, we will be getting the equation like this. We will get the equation for the first mass like m x1 double dot plus 2kx1, and we will get kx2 is equal to 0. So let's treat this as equation first. Okay, and for second mass when we will write a free body diagram. So for second mass we have again m, we have again m, and we have this spring will be compressed, so it will give a force upwards. Okay, it will give it a force like this. It will be, it's again k, and its displacement is there x2. Okay, kx2. Okay, and we have to give fictitious load in the direction opposite to the direction of the motion, mx2 double dot, and we have the direction of motion like this. Okay, we have x2 of t. So here in this point, this spring will be elongated. So when it will get elongated, it will give it a restoring force like this. Sorry for this thing. It will give it a restoring force like this. Okay. So this and this will be balanced. It will be K2. It will be Q2 of x2 minus x1, and this will be m. Okay. So when we again start writing uh, the summation of the force along y-axis equals 0. So it's again FBD for M2. Okay. Before it was FBD for M1. So when we write again summation of Fy is equal to 0, we will obtain an equation like this, mx2 double dot. I'm not writing it in detail because you guys know that how we have to do summation of forces. X1 is just simple, plus 2kx2 should be equal to 0, and we will denote this equation as equation 2. So as I already said in last class, we can write this system of equation in terms of a matrix form. So we can have a matrix form like this, where we can have m 0 0 m 2 degrees of freedom. So matrices will be 2 by 2. We have x1 double dot, we have x2 double dot, and we have to write for this k. First will be 2k, it will be minus k, it will be minus k, and it will be 2k again here. Okay, so this will be like this, and we have the two displacement from x1 x2. Since it's the free vibration problem, no forces are acting on the system, so we have 0 0. This is the system of equation that we will obtain for our 2 degree of freedom system. So we can write it as system of equation for 2 degree of freedom system. Okay, so now we are quite get the modal frequencies and mode shapes of this system. So we'll make one assumption, that is assuming same as I assumed last week, that the solution to be harmonic, as assuming solution to be harmonic. Okay, harmonic of form. So harmonic So solution to be a harmonic form like displacement at any function xi of t at I is equal to 1 comma 2 is equal amplitude at that point xi cos omega t plus phi. Okay, omega is the natural frequency and plus phi is the phase angle. And here I am writing that I is equal 1 comma 2. So let's treat this as our equation third. Okay, we are assuming the solution. Okay, just a small assumption, making note this. Okay, this one, this thing. So again, when we will do the same thing here, we will find, sorry, we will find x dot and x double dot. Xi dot of t, I told you it will be xi minus xi omega. Okay, sine omega t. Omega t plus phi, it will be one thing. And we actually require x double dot of I of t will be equal to, it will be minus omega square xi cos omega t. Omega t plus phi, actually we can write it in a more compact form like this. When we substitute back xi, it will be equal to minus omega square xi cos omega t plus phi from equation third is again xi of t. Okay, for all I is equal to 1 comma 2. So we will treat this as equation 4. Okay, when we substitute equation 4 in equation 3, we obtain what we will obtain is we obtain this thing. We obtain this matrix. We obtain minus m omega square. I showed you this last time in full detail, so I'm writing it directly to save some time here. Okay, 2k, and it will be k minus k. In fact, it will be minus k here again, and we are having minus m omega square plus 2k again here. Okay, this will be our this matrix. Okay, and we will be having, so it will be x1 of t, this will be x2 of t. Okay, equal to 0 comma 0. So to have a non-trivial solution, we assume that the determinant of this left hand side matrix should be equal to 0. So actually that was just the eigenvalue problem that we have. I already told you that eigenvalue problem is this. uh, K minus m omega square. We write determinant of this should be equal to 0, or we have determinant, we write it like this, and we have this thing minus m omega square plus 2k. We have minus k, we have minus k, and again here minus m omega square plus 2k, which should be equal to 0. This is eigenvalue problem. So when we will solve this equation, we have, so we have here minus m omega square plus 2k whole square minus minus plus minus k square is equal to 0. When we will expand this, we have m square omega power 4 minus 4km 4km omega square plus 3 square plus 3k square is equal to 0. So we have this equation 5. Okay, so solving equation 5, we get, so we will get two things for omega as omega 1 square. Okay, so we will get omega 1 square to be minus b, so minus is minus, plus 4km minus b, plus root under b square. Okay, b square is 4km whole square minus 4ac. 4a is m square and c is 3k square divided by 2a. Okay, we have 2a is 2m square. Okay, this is one thing. And then we have omega 2 square to be 4km, again same thing. Wait one second, I will do it a little bit in shortcut. This is same thing. I have this same thing here, but we have one small change here to be minus. Okay, this thing. So when we will solve these things further, so this will be equal to k by m, k upon m, and another we will obtain 3k upon m. Okay, so two natural frequencies we obtain as omega 1 to be equal to k by m, and omega 2 to be equal to 3k by m. Okay, this is two modal frequencies. Since there are two degrees of freedom, there will be two modal frequencies. What is happening to this? Okay, this will treat as sixth equation. Okay, modal frequencies. This is the one thing. Okay, then we have to get the mode shapes. Okay, for mode shapes, what we have to do is, um, we have this problem here. So equation alpha here. Okay, so in equation alpha, we have to substitute we have to substitute 6. Okay, so mode shift 1. Okay, for mode 1, that is omega 1 square is equal to k by m. Okay, from 6th, when we will proceed with this thing. Okay, so we have this is equal to k by m. Okay, k by m. So this will be equal to, so this is minus m k by m plus 2k minus k minus k. It is minus m k by m plus 2k. So this is x1, this is x2, and this for mode 1, okay, is equal to 0, 0. When we try to solve this thing, okay, we will get our this one. Mode shape says this like both will be equal to x1 is equal to x2 is equal to 1, okay. So this is the relative displacement. So if we want to write it in the actual form, we will write it as so because we divided it by this thing x2, it's the ratio. So first mode will look like this. First mode will be x1 of t, x of t, and its mode 1. It will look like something this. Okay, we have to write it as amplitude in x1 in mode 1, and it will be equal to cos of and omega t natural frequency in that mode. It's k by m of t plus phi. Why this x cos omega t plus phi comes? Because we already assumed the solution to be harmonic, and it will be sorry, x1 of mode 1 again equal to cos k by m of t plus phi. So why are these coming to be equal both entries? Because above x1 and x2 is equal to 0, okay? Here this x1 and x2 is equal to 0. Similarly for second mode I am not writing the whole derivation. Second mode we can get for second mode put omega equal to omega 2 in equation alpha, okay? We will get x1 is equal to minus x2, okay? Remember this. So for second mode we will get x second mode of t will be equal to here x1 of 1 cos, here it will be natural frequency of this mode 3k by m, okay, 3k by m t plus phi, okay, and it will be x1 magar minus times, sorry it's not 1 here, it's 2, it's 2, it's root 3k by m of t plus phi, okay. This is the thing like this. So the second mode would look like this. Okay, these are the solutions. Mode 1, mode 2. Okay, here's the solution for mode 1 and mode 2. So we have the first question. We will move to the second question. So second question is, determine the stiffness matrix of the frame shown. Okay, we have to neglect the effect of axial stiffness in members A, B, and C. Okay, so we have to put this. Okay, I have to mm, I have to find stiffness matrix K of frame A B C. Okay, we have to neglect actual stiffness of members, actual stiffness of members A, B, and C, A, B, and B, C. So this is the assumption given. So in the problem, you can clearly see that this is a 3 degree of freedom system. Okay, here. Okay, here at point B, I have given it. Okay, so 3 degree of freedom system. So I will have some enlarged view of this. So we will have x displacement. We'll be having x displacement. We'll be having y displacement, and we will be having a rotation also at that joint. Okay, so these are 3 degrees of freedom. So we will be having 3 by 3 stiffness matrix. So what we have to do, we have to do procedurally, as I told in the last session, that for deriving the stiffness matrix for multi-degree of freedom system, we have the each element of a stiffness matrix is represented by Kij. So Kij is actually the force produced at ith degree of freedom because of the because of the displacement, unit displacement given at jth degree of freedom, and all the other degrees of freedom are restrained, or the displacement at all the other degrees of freedom is zero. Or it can be force produced at force produced moment produced at ith degree of freedom due to unit rotation at jth degree of freedom and zero rotation at all other degrees of freedom, if it is the rotational degree of freedom. Or if it is a translation degree of freedom, we have to give the unit displacement to jth degree of freedom and get that in force produced at ith degree of freedom. So I will again write here for your convenience here what I and j denote. It is uh, force at the rate of ith degree of freedom, ith degree of freedom system, when unit displacement at jth degree of freedom. This is the formula. This is what is contained in this uh, Kij term. When unit displacement at jth degree of freedom and zero displacement at all other degrees of freedom. Okay, all other degrees of freedom. So we will proceed this problem in the similar fashion by giving unit displacement first along x and zero displacement along y and zero rotation along theta direction. And then in the similar manner, we will give unit displacement along y and along x zero displacement and along theta zero rotation. Then we will restrain both x and y directions, that is give zero displacement along both these directions, and give along theta direction we will give 1 radian this rotation, and we'll find the forces in members, forces required at these degree of freedom. So firstly, one more thing I want to note here is, in the figure I have shown this here in the figure, you people can see that it's a member with a Young's modulus E, stiffness I, yeah, moment of inertia I, and length L. So if we have rotation theta 1 and theta 2 and m1 m2, it is actually the sign convention which is followed: f1 and f2 positive, w1 and w2. So for example, at one end, if I give uh, W displacement along this positive direction. So I will have a moment is developed like this with the moment that will be developed at this end will be 6EIW1 by L square. It is actually 6EI delta by L square. In structural analysis, you people would have read in the topics, sinking of supports and all the other things related to this. And similar moment will be developed 6EI W1 by L square when we give a displacement of W1 at this end. This is near and this far and same moment is developed, and the reaction that will get developed is 12 ei w1 by l cube and minus 12 ei w1 by l cube. It's just a simple thing. If we can also derive it, but it's not required here because we are not dealing with the structural part of it. We have to only get the stiffness matrix of this system. This f1 and f2 have to be in opposite direction because they have to make a couple of 6 EIW1 by L square. Okay. So similarly, another formula, if we are not giving W1 displacement at near end, we are giving theta 1 rotation at near end. The moments that will get induced are 4 EI theta 1 by L, and another will be 2 EI theta 1 by L. So we have a reduction factor of 1 by 2 here at the fixed end. And moments that will get forces that will get induced is 6 ei theta 1 by L square at near end, and as F2 will be minus 6 ei theta 1 by L square. So we have to use the same formulas in our members A, B, and BC to get our forces Fx, Fy, and M theta. So in firstly, what we will do, and since A, B, and BC we can consider both as beams, and actual effects are to be neglected. Okay, I already wrote A, B, and BC can be considered as beams. Okay, so we have to see that necessary forces that will cause displacement along one coordinate while maintaining zero displacement along all the other coordinates of the beam. Okay, the ends A and C are fixed, and hence the joint B will have three possible displacements x, y, and theta that I already mentioned. Okay, so we are now first we will have Fy is equal to 0, and we will have moment m theta is equal to 0. We will find Fx that will be produced when we will give delta is equal to 1 unit along x-axis. Okay, so I will make this again here. So we have to give, this is the frame like this. Okay, so to this frame give delta is equal to 1. Okay, delta is equal to 1. So this will be turned to this direction and this direction. Now there will be a elongation delta is equal to 1 in member AB also. Okay, this is A, B, C. So it will call AB will be having also the axial stiffness, but in the question it's already mentioned that axial stiffness has to be ignored. So we have to ignore this axial stiffness. So we have to take only BC member only. So delta we have to find Fx produced at that point. So taking this elongation of this member, okay, taking this member only. So we have, I will make it by a different, this is like this. Okay, this like this. So When we give delta equal 1, delta is equal to 1, so we will have a force like this induced here, a moment induced here. So it's already here 6 EI. It will be moment will be 6 EI, delta is 1, so it will be L square. Okay, so it is having EI and 2L. Okay, you have to keep that in mind. E comma I comma 2L. Okay, so it will be having like this, and one more moment will be like this here. Okay, sorry, this is not like this. It will be again here. M will be equal to 6 EI by L square, and E and I both are different. L is different, E and I is same. Okay, and forces that will be getting developed is like this. We will get force Fx, and we will have minus Fx like this. Okay, clear to you people? As I already mentioned. So in the formula here we have Fx 12 EI delta by L cube. So it will be 12 EI delta is 1 by L cube. L cube will be different, and it will be again here 12 EI delta by L cube. Okay. So what is the force that will be developed? Fx will be equal to, but we have to take this force as positive because the force is getting generated in the direction in which we have applied the displacement. We applied displacement in this direction, positive x direction. Applied displacement in positive x direction. Okay, and force is also getting developed in that direction also. So Fx will be equal to 12 EI by L cube. Okay, so it is actually a first element. Okay, so it will be 12 EI by L cube of BC member. Okay, we have to enter the quantities corresponding to BC member. 12 E is same, I is same, L cube is 2L. Okay, 2L ka whole cube. uh, this will be equal to 3I by 3EI by 2L cube. And other things that gets developed at that point is Fy is equal to 0. It's that, and we also have a moment there, 6 EI by L square. Okay, or BC. M theta will be developed there. M theta will be developed 6 EI by L square of BC. Okay, and it will be when we give this thing, it will be 3I by 2L square. Okay, because L we have to put 2L. Similarly, similarly we will give delta along y is equal to 1 unit and 0 displacement or rotation along other degrees of freedom, that is y comma theta tend to be 0. Okay, so for that thing, when we will make that thing, it's like this. It's the same frame like this. Along y direction we have to give unit displacement, so it will be, sorry, so it will be displaced like this thing. Okay, so we have this delta y to be equal to 1. We have a frame from this side. So again, along y direction we will be having axial stiffness of member BC, but we have to neglect that one as it's already mentioned in the question. So it will get elongated like this. So again, when we take the bigger picture of this thing at joint B, okay, when we take a larger picture, so we will have, okay, like this. This is our beam. This is A, B, and it is getting displaced like this. Okay, it is having delta y equals 1, delta x equals 1. So it will, and the moments of this type will get induced in it, and one more moment like here. Okay, this, and it will be 6 ei delta is 1 by L square. It is 6 ei delta by L square, and we will have forces like this. Okay, Fi will be equal like this, or balancing of forces, we will be having forces like this. Okay, forces are 12 ei delta is 1 by L cube. Okay, this will be the Fy developed there. This will be minus Fy here. I'm not writing it again here. So this these things will be generated in our beam AB. Okay. So writing this thing in a detail, we will have, in this thing we will have Fx0 as I already mentioned. Then we will have Fy to be equal to 12 EI delta is 1 by L cube, but it is of member AB. Okay. AB, and we are again having AB equals, so I have to write it as, it is E comma I comma 2L. Okay, no, it's not E, it is E, it is 2I comma L. Okay, it is having different properties. So when we induce that properties into it, we get 24 EI by L cube. Okay, L cube. And for m theta, you people will be seeing here m theta is 6 EI delta by L square getting induced there. So here it was anti-clockwise moment. It is clockwise moment. So we are taking here as per the sign convention. So sign convention here. So this is positive, na? Anti-clockwise moment is positive. So sorry, anti-clockwise moment is positive. Anti-clockwise moment is positive. So here it was getting anti-clockwise moment, that is m theta is positive. Here it is getting clockwise moment, so this will be negative. Okay, so m theta generated will be negative. It will be, m theta will be equal to minus 6 ei delta is 1 divided by L square of b L square, and it will be of AB part, and m theta written will be, when we will get m theta for this, we will get minus 12 ei, because I is 2I. Okay, L is all as itself L square. Okay, L square. So finally finally we have theta to be 1 radian, and along x and y we have del x equals 0 and del y equals 0. Forces forces required to maintain this position. this equilibrium position are, I will not again repeat it how we can get fx, xy, and theta here, because I already written here. If we give a unit displacement, if we give a displacement theta 1 at one end, moments 4 ei theta 1 by L will be getting generated, and forces 6 ei theta 1 by L square will be getting generated. I will be writing it as it is. So we will be getting fx. So we will be getting fx will be equal to 6 ei by L square of AB, okay. So it is I having 2i, so 3 ei by L square will be one thing, and Fy will be equal to minus 6 ei by L square of BA. Okay, it will be equal to minus 12 ei by L cube. Okay, so these things, and m theta will be m theta. M theta will be the summation of the two, one for BC and BA. One will be 4 ei by L. That will be for BA or AB, plus 4 ei by L, and it will be for, sorry, it will be for BC. Okay, these two things. When we will substitute the corresponding quantities, we will have 10 ei by L. You have to do this calculation yourself by substituting I to be 2i in AB case and L to be 2L in BC case, 10 ei by L. So we are having all the required quantities. Finally, we can write the equation of this stiffness matrix as force. We have force developed is stiffness matrix K times displacements at that point. Okay, so we have what we have displacements as, we have force Fx, Fy, Fz. Okay, okay, we have K will be then equal to, sorry, K will be this matrix. Okay, and this is X, Y, and theta. This is m theta. Sorry, this is not, because along that direction we get moment developed, in theta direction we get moment developed, m theta. So this will be kxx, kxy, kx theta. Okay, this will be kx theta. Okay, then we will have kyx, kyy, ky theta. Similarly, this will be k theta x, k theta y, k theta theta. Okay, these are the nine statistics components, and we already derived them. Where we have, where we firstly we obtained for xx. This was uh, actually it was stiffness force that gets developed because of unit displacement at x and all the zero displacement at all other degrees of freedom. This was kxx. Actually, this was kxx. Okay. Then similarly, this was k. This is we are giving unit displacement. This is x and this is y, kyx. Okay. Similarly, this is k. We are giving it x. This is k theta x. You people are getting the point. And in other things also, we got this. This was k xy actually. This was kyy actually. Okay, this was m theta y actually. Okay, similarly we are having this as m theta theta, m theta theta. Okay, this was m x theta, not theta theta, it's k. This is k given at y, k theta y. Okay, similarly we can write k theta theta here. It is k theta x. Okay, all the other things you can write in the similar fashion. When we substitute all these values in this, we will get a stiffness matrix. Our stiffness matrix like this one. K will be equal to like this. Okay, so we will be having first component we will be having as this 3ei by 2l cube. 3ei by 2l cube. Okay, this one. Then this is 0. We have this 3i by 2l cube. Okay, 3i by 2l square. Okay, this will be 0 again. This is 24 ei by l cube. Okay, this will be 24 ei by l cube. This will be minus 12 ei by l square. Okay, so this will be equal to 3 ei by 3 I by 2l square. Okay, this will be here like this, and this will be symmetric minus 12 ei by l square, and this will be finally equal to 10 10 ei by l. Okay, here is the 10 ei by l. Okay, you people will be getting it easily from this. Okay, this thing. So finally our stiffness matrix, if we write it in a compact form, K will be equal to ei by l cube, and other things like this. We have 3 by 2, 3 by 2, 0. We have 3l by 2, and we have this diagonal as minus 12l. This is as 12l square. We have 24. Okay, other things are symmetric, 12l, 3l by 2, and 0. This is the required stiffness matrix of our frame. Matrix of frame. Okay, so we derived the stiffness matrix for this type of frame problem. Okay, then we have another question here, problem 3. Okay, so we have to so we have this 3 degree of freedom system M1, M2, and M3. So for this 3 degree of freedom system, we need to derive this free vibration equations of motion and also natural frequency and mode shifts. So let's do this question quickly and then we will stop. Okay. So equation of motion we can write as equation of motion for 3 degree of freedom system. Okay, we have this is mx double dot. Okay, plus kx is equal to f force. Okay, force vector. So for this system of equation, we can directly write because I will not be again doing it, writing the free body diagram for each mass and then writing the equation of motion. I will directly write the mass matrix. That thing is an exercise for you people. We derive it carefully one by one. Equation of motion for single mass m 0 0 0 m. Okay. One more thing, I am assuming that m1 equals m2 equals m3 equals m, and k1 is equal to k2 is equal k3 is equal to k. Okay. These are the assumptions we have to make. Okay. Okay, these things. So again, we have in here mass matrix. This one, stiffness matrix will be K. K will be like this. So K will be K1 plus K2. It will be 2K. It will be minus K 0 minus K 2K minus K, and it will be K. It will be minus K and it will be 0. We're having this equation. Okay, we get mass matrix and stiffness matrix as well. Force vector F is equal to, we have F1, we have F1 of t, F2 of t, F3 of t, and we assume all three to be equal to 0. Okay, because it's free vibration problem. Okay, so free vibration problem. So again, I told you how, as we did in the first problem of the session, we have to solve the eigenvalue problem like this one. Solving eigenvalue problem. Solving eigenvalue problem, that is k minus m omega square, k matrix minus m matrix omega square of x should be equal to 0. So for that thing, determinant of this thing, k minus omega square m should be equal to 0. So when we will solve this problem, k minus m omega square, we will have this thing. One more thing we will doing that, we will be put omega square is equal to alpha. Okay, we will have a little bit ease while doing computations, because otherwise it will get the power of omega, we will get the power of omega to be sixth power, and then we will wonder how we will solve sixth power polynomial. I am making the substitution omega square is equal to alpha. It will make the polynomial to be cubic one, and then we will be solving. When I substitute k matrix here and mass matrix m here, so I have written small m here, so I will be writing small m here again. Okay. So when I will do that thing, I will get cubic polynomial of alpha cube minus 5 alpha square plus 6 alpha minus 1 is equal to 0. Put here and solve. This is our equation 7, okay? Equation 7 and equation 7 and solve equation 7, okay? We will get this equation. So solving this 8, solving equation 8, solving equation 8, we will get alpha. We are not putting alpha, we are putting actually m omega square by k equal to alpha. This will reduce our computations very much. So we will get alpha to be equal to alpha values are alpha 1 will be equal to 0.198, 0.198. We will get alpha 2 equal to 1.55, 1.555, and we will get alpha 3 equal to, because it's cubic polynomial, we will have three equations, 3.249. Okay, so correspondingly the natural frequencies to these modes are omega 1 will be equal to, because we have now alpha I is equal to m omega square by k. Okay, so we will be having omega I square by k. Okay, so omega 1 will be 0.445 on root k by m, and omega 2 will be equal to 1.247 on root k by m, and omega 3 will be equal to 1.802, 803 in fact, on root k by m. Okay, these are the natural frequencies corresponding to three modes, because we are having 3 degree of freedom system modal frequencies. So if I start doing the same procedure as I did in the problem first, like this was a problem first. I will do the same procedure here. Once I got this omega 1, omega 2, then x1, move for mode 1, mode 2, mode 3. Same procedure I will follow here in this equation. So once I follow the same procedure, I will get all the three required mode shapes. Okay. So I am not doing it in the again here. I will just write the mode shapes that we will get. So mode shapes, mode 1 we will be getting mode 1. I will again write mode 1. This is equation 7. Put omega equals omega 1, and we will have mode 1 vector as x1 of x of 1 as x 1 of 1, and these will be 1, 1.8, 1.0, 1.8, and 2.3. Okay, this will be one mode. Okay, similarly mode 2 put omega equals omega 2, and we will be having x2 as x2 mode vector as x1 of 2, and it will be, these ratios will be 1 0.44 minus 0.80. Okay, this is x mod 2. This will be mod 3. Mod 3. Put omega equals omega 3 in equation 7. Okay, so in equation 7, okay. So we have x of 3 will be equal to x1 of 3. We will be having values here 1.0 minus 1.2 and 0.55. This will be the mode shape. Okay, correspondingly, if we want to plot that thing also, we can do that one. I'm doing here it. So first mode shape will be like this. So for example, we have this no displacement yeah, axis here. So first mode will be like this. So first is 1, again and again. Okay, we have this one here, and this one here. Okay, second mode will be like this. Second mode will be if we have like this, no displacement. One value is negative. Okay, so this value is negative. We have to travel to that value. Okay, then we have no, the second value is also positive. Sorry, second value is also positive here, but after that we have third value negative. Okay, we have this is x1 of 1, this is x2 of 1 mode, this is x3 of 1 mode. Okay, and then again we have we have x1 of second mode, this is x2 of second mode, this is x3 of second mode. Similarly for the final mode, we have this one positive 1, then we have negative downwards minus 1.2, then we have again positive 1 here, positive 0.55. So we are having x1 of mode 3 here, we are having x2 of mode 3 here, and we are having x3 of mode 3 here, whose values you can get from these equations. X1 superscript 1, X superscript 2, and X superscript 3. Okay, these are the basic things you have to learn while deriving models for Kinsey's mode shapes. Okay, so we discussed three problems, three major problems. These were lengthy problems. So you practice these problems at your place also. Then you will get expert in a multi-degree of freedom system. One more problem is here. This is an exercise problem for you people. Thank you everyone for joining. Exercise problem. Okay, thank you.
Hello,
Yes, hello.
Danish sir.
Yes, yes.
So have you seen the last assignment related to chimney?
Okay.
Have you seen the assignment of week 10 related to chimney?
No, no, I haven't went through the assignment yet.
Sir, next time if you will need, can you review that or can you solve that for me?
Okay, I will try to see the assignment. Which assignment number?
Assignment number 10, I think. Week 10 का ही है ये.
Okay, assignment 10, I will see. Okay, no problem.
Actually,
Okay.
I was
You
having
are
a
ha-
problem with that.
you are
The
having
chimney
any
was
doubt
just,
in today's session? Multi-degree of freedom
no,
system?
no, sir. Actually, I have also done MTech from Jamia Millet and I have learned this type of
Okay, okay,
problem.
then no
So
problem, no problem.
I haven't felt any difficulty on this type of problem.
Okay, okay.
Just I want the solutions of the last week 10 assignment. Question number 1, 2, 3. They are on continuously same question divided by
Okay,
3 parts.
okay, okay, no problem. Okay.
Thanks a lot.